Okay, so hello everyone. In this video, we'll be looking at an exercise in which we convert a DFA to an equivalent regular expression. So just as a reminder, there are actually two algorithms that exist, or at least that I know of, that can be used to convert DFAs or FAs in general to regular expressions. The first one is the K-path conversion algorithm, which is a bit of a recursive algorithm. And it's actually quite nice because it can be the its recursive property can be used to easily prove its correctness. So that's typically why it's presented. Um, to be honest, it's a bit complicated to work through, and sometimes there are extra steps that um, can be easily skipped if you're using another method. And so the other method that I'll be using to convert this DFA to a corresponding regular expression will be the state reduction algorithm. Okay, so in the state reduction algorithm, the general blueprint of the algorithm is to do the following. It's to eliminate states while preserving the logic of their transitions. So doing this elimination or this sort of doing this elimination for every intermediate state in the FA until the stopping condition until you get a final FA that looks something like a start state, a regular expression as the label of the transition. So we'll see how that's possible in a second to an accept state, right? And so the idea is once you get to something like this, because you've preserved the logic of the transitions, you've just sort of eliminated the intermediate states, then this regular expression should be equivalent in terms of describing the regular language as the initial FA that you started with. So maybe in case you haven't seen the the description, the full description of this algorithm, it might be a bit ambiguous or vague um, to think about just eliminating states while preserving the logic of their transitions. That's a bit of a vague and high level statement. Essentially, the general idea behind how this works is, you might have in your FA, so either an NFA or a DFA, you might have some triple of states where maybe um, this first state Q1, Q2, and Q3 are sort of connected with some transitions. So for instance, Q1 to Q2 can be achieved with an A, reading an A. Q2 to Q3 can be achieved reading a B. There might be a self loop on Q2. And then there actually might also be a direct loop from Q1, or a direct transition from Q1 to Q3. So the idea in the state reduction algorithm is to get rid of all states which are not the start state and the accept state. And so you do this by removing intermediate states one by one. So for instance, if I were to want to eliminate Q2, so eliminating Q2, what this would look like is, I would rip out Q2. So I would rip out Q2 from my FA, but then I would have to somehow preserve the logic of Q2, meaning that I should preserve um, the paths that Q1 allows my FA to take. So in this case, what Q2 allows my FA to do is to transition from Q1 to Q3 by reading an A, reading any number of A's, and then reading a B. right? And so the way that you can represent that once you rip out Q2 is by using a regular expression as the label for the transition between Q1 and Q3. So if I eliminate Q2, then I get a new label for Q1 to Q3, which will be, well, how can I get from Q1 to Q3? Using Q2, I can read an A, then I can read any number of A's because of the self loop, and then I read a B, right? I can also alternatively go from Q1 to Q3 reading a B. So now you can kind of see there's like an or here. So either I can do this or I can do this. And so then because now we're allowing regular expressions as part of the labels of my transitions from one state to the other, I can just add this other option um, to a single label of my transition from Q1 to Q3 by saying, well, I can either do A star B, or I can just read B, right? And so this is the sort of idea that's going on behind this general hand-wavy statement of preserving the logic of transitions. And in general, essentially what you're going to be doing is you're going to in the body of this loop, you're going to remove one state at a time, making sure that you preserve the transitions for all pairs of states that use the state to eliminate, the state to eliminate um, as an intermediate state. So, I mean, maybe in this case, the only thing that Q2 allows is this kind of path. But I mean, realistically, it's very possible that I might have, um, other states like Q5 and Q6, and maybe Q5 goes to Q2 via a B, and then Q2 goes to Q6, maybe via a regular expression because I maybe already eliminated something in my FA, so maybe via B star. In which case, now you have to account for every possible kind of pair of states, which use the state that you're eliminating as an intermediate state. So for instance, I have Q1 to Q3, but now I should also account for Q1 to Q6, for Q5 to Q6, and for Q5 to Q3, right? Because when I'm removing the state, if I want to preserve exactly the same FA in terms of what language is being accepted, then I want to preserve all the sort of possible transitions I could have taken if Q2 had actually been there, right? Okay. So hopefully this is a good like refresher if you didn't know about this algorithm yet. Now what we're going to do is we're actually going to run it on the DFA that we're given. So we want to convert this to a regular expression. And so actually the first thing that we're going to want to do is we're going to want to make uh, one start state and one accept state. And in fact, we kind of want to ensure so that this algorithm kind of works out that uh, ensuring that the start state is different from the final state, okay? So how do we do this? Well, we basically just use epsilon transitions, right? So if in in a different NFA, you had maybe 3 start states. So this is possible for some um, definitions of NFAs. Then, you can just add an extra new start state, a single new start state, and connect to the other start states using epsilon transitions. And then similarly, if you have multiple accept states, then you can sort of convert this to an FA that has a single accept state by saying, well, here's my single accept state. Let's make these guys non-accept states, and let's use epsilon transitions, right? Because remember, epsilon transitions just allow me to jump from one state to the other for free without reading anything. Okay, so in practice, while like in principle, um, the FA that had three accept states here looks different than the FA that has a single accept state here with these three guys non-accept states. In practice, they're actually going to accept the same language, right? So we kind of have to do that for the FA that we see here. So let's take this FA and do exactly that. Take this FA, do exactly that. So let's see, I'm going to add a new start state, and I'm going to add a new single accept state. This no longer should be an accept state or a start state. And I'm going to add my epsilon transition for the start state and also for the accept state. Right, so this is step one, right? Okay, now step two, and actually the all the steps from now on are just going to be about eliminating states. So the first thing that I actually notice is that I have a dead state, right? So a dead states I can actually just remove without um, losing any information because dead states don't actually allow me to accept strings. So I can delete dead states. I can also, if I had like an unreachable state, like Q6 here, I can also delete unreachable states. Okay, cool. Okay, so I've deleted dead states and unreachable states. Now I actually have to do a bit of work in terms of removing intermediate states. So let me recopy only this part. So this is my new FA. Now let's see, let's delete this state. So if I want to delete the state, then I need to account for the logic that it allowed. And in this case, the logic that it allowed was that it allowed Q0 to go back to itself, right? How did it allow this? By allowing Q0, by allowing the FA from Q0 to read a B, and then to read either an A or a B. So then that means that if I remove Q1, then I should have, wait, let me actually just copy. If I do this, then if I remove Q1, I should get a self loop on Q0 because that's the logic that um, that is allowed using Q1 as an intermediate state, where I can start with a B and then read either an A or a B to go back to Q0. Now, again, I'm going to do the same thing, in this case, deleting Q2. I mean, you could, of course, delete Q0. I'm going to do Q2 because it seems simpler, right? There are less connections. So if I delete Q2, well, the only thing that Q2 is allowing me to do is, again, for Q0 to go back to itself, right? But in this case, it's allowing that by allowing the FA to read from Q0 an A and then a B. So then if I delete Q2, if I delete Q2, then that means that I should add extra stuff in the self loop to Q0 because you're allowing an additional way to go back to Q0, right? So I should also have a self loop for um, A and then B, right? Because I can read an A, so I describe an A and then I read a B, so I then describe a B, right? So then I delete this guy. And now, okay, this is very nice, right? Because now this is the last state that I have to delete. So if I want to delete this state, then I just have to preserve what this state allows me to do to go from the start state to the accept state. And what this really is allowing me to do is to go from the start state to the accept state by reading uh, any of by reading strings that look like either this or this any number of times, right? So what that means in general is that self loops become star operators. And in particular for here, that means that if this is my start state and this is my accept state, then what Q0 allows me to do is to read an empty string, then to read B, A plus B, or AB any number of times, and then to read an empty string, and then to go to my accept state. And in practice, if you have some regular expression empty string, then it's the same as it's equivalent to that regular expression without the regular expression that denotes the empty string. So that means that if I simplify this just a little bit, then I get B, A plus B star, AB, whole star. And so that means that the regular expression R, which is equivalent to the DFA that I started with here, was B, A plus B star plus AB, right? And I think if we just look at the original DFA, this will probably make some sense. So this is what we got in terms of regular expressions. So let's see, this is saying that you're going to recognize any string that's like any number of interchanging between AB and B, A or B whole star. Wait, I'm noticing that, okay, somehow I introduced a star here, which was incorrect. Hopefully you spotted that. Yeah, I don't know why I just added a star there. Okay, so that's not quite right. Um, And this seems to be true, right? Because to accept a string, it can have, B and then AB, and then it can have A and then B, and then you can go through these guys any number of times, right? As long as you get to an accept state, as long as you come back to the accept state, which is kind of why you need these two guys to be there, right? And for something like AA to not be there, because then you would go to a dead state. So that's why just eliminating the dead state was good enough. Okay, and so that's how you convert this DFA to an equivalent regular expression.